Okay, here's our third example of Faraday's law, and this one's a little bit different. So in this situation, we've got a magnet and a coil, and this is the north pole of the magnet, and that's the south, and this is our coil of wire. Now, this is scene one, or this is the initial state. Down here, this is the final state. What's happened is the magnet has flipped. The coil hasn't moved. The magnet has spun over. So this is the final situation here. Shall I just grab that word and move it over here? Okay, so the question is, what is the average EMF generated across the ends of this coil if we spin this magnet around 180 degrees? Now I'm going to give you some data, of course, to allow you to solve this. So let's say that our area of our coil is 0.02 meters squared. And let's say that the magnetic field strength in this situation passing that the coil is exposed to is, we'll make that 1.8 Tesla. So what's actually happened is that our magnet has spun around and done a complete 180. So this is now north and this is south. The amount of time that it took to do that 180 spin, the time equals 0.01 second. So it spun pretty fast. What we want to work out is the average EMF induced in the coil between this state and this state. Now, this is where our normal for our coil is going to come in handy. So here's our coil over here. Whoops, bring it back. So here's the face of our coil. Now, in the first situation, remember, field lines come out of a barb magnet and out of the north pole of the barb magnet and go into the south pole. So in this arrangement, the field lines are actually running in this direction. And so we can summarize that direction through the coil as a simple arrow pointing in that direction. So that is the direction of the field in the initial state. When the magnet is spun around, remember the magnetic field lines go into the north and out of the north and into the south. So in this situation, they're coming into the south pole. So they're re-entering the magnet there. So the direction of our magnetic field through the coil is in that direction. Now the coil hasn't moved. So let's assign the normal as right angles to, let's make it a bit thicker, at right angles to the face of the coil. So there's our normal, and the coil hasn't moved, so our normal will still be in that direction. But look at the direction of the magnetic field in both cases. So here, in this first scenario, the angle between the normal and the magnetic field is 0 degrees. So here, theta, the angle between the magnetic field and the magnetic field of the normal is 0 degrees. Here, the angle, because they're facing opposite directions, the angle is 180 degrees. And for those of you who aren't sure about this, if you type in the cos of 0, we know that the cos of 0 is 1. Sorry, the cos of 0 is 1. The cos of 180 is negative 1. Okay, so let's work out the EMF. Now, once again, the EMF is going to be, sorry, I didn't tell you how many turns of wire there are. This time there are 30 turns of wire. So N equals 30. So the EMF is equal to N times the rate of change of flux, or the change in flux over the change in time. Let's work out a change in flux. So the change in flux is the final flux, take away the initial flux. Okay, so what we now need to do is work out this flux. And once again, we're going to use the flux formula. So for the final flux is this situation. This is the final state. This is when they're pointing in opposite directions. The normal to the coil and the magnetic field line are pointing in opposite directions, so the angle is 180 degrees. So here it's going to be, the flux is going to be B times A, so it's going to be 0.02 times the area, sorry, that was the area, times B, which is, I thought I wrote it down somewhere. I couldn't have. Okay, I thought I did. All right, so the magnetic field strength will make it 2 Tesla. Okay, so there's our magnetic field strength, 2 Tesla in both cases. So it's going to be the area times 2. So that will be 0.04. So that's our flux through the coil. Okay, so there's going to be times cos theta. Now here, cos of 180 degrees is -1, so the final flux will equal -0.04. On the other hand, the initial flux, which was just the scenario in the first situation, all the numbers are the same. There it is there. Sorry, ignore that. All the numbers are the same, except that the angle now is 0 degrees. So it'll just be 0.04. So the final take away the initial is going to be -0.04, take away 0.04, and that will equal 0.08. Or -0.08, I beg your pardon. That is our change in flux. And we now know that the time is 0.01 seconds. So if I can find a bit more room here, I might have to do it up in this right top left-hand corner. So the EMF is going to equal N, which is 30, times the change in flux, which was the final, take away the initial, which was the final, take away the initial, which ends up being -0.08 Webers, divided by the time taken, which is 0.01. And if we calculate that, that is 240 volts. It's actually The numerical answer is actually 240. There should be a negative sign in front of it to be technically correct. However, once again, that negative sign doesn't really mean anything to us at the moment, but it will when we start talking about the direction. So here's an example of a problem where the coil wasn't moving, but the magnetic field was. But remember, as long as the flux is changing through the coil, it doesn't matter how that is achieved. If it's changing, you're going to get a voltage induced in the coil. Thank you.